All right. Sure, we'll get a few more. That's where we leave off. So analysis of variance, we're utilizing variances to determine if means are different. And the key is that we're going to compare differences of our group means to a grand mean and scale that to overall variance. So the more different our grand means are from each other, the farther away that they are from the grand mean itself. All right. So we're going to use the F statistic, and we have the assumptions. We already said that it is same. They're the same assumptions as a t-test. So data are random and independent. Data are normally distributed within each group, and data are the variances are equal. And there's a specific term here, and there you should kind of write it down and know them. Homoscedastic means that we have equal variances. Heteroscedastic means we have unequal variances. So how I drew the graph up on the board with the error bars, if those things should be equal among all of our groups. It's a pretty big assumption for us. Those are equal. If they're equal, then we can utilize our group averages to calculate our between group variation. So of our assumptions, definitely random and independent, we plan for it when we collect our data. The normality within each group, that is ANOVA is robust against that violation. Oops. ANOVA is robust against that violation. So if we have slight deviations, or if we look at it and we have maybe one or two of our groups that look slightly non-normal, no big deal. ANOVA can handle it. All right? But ANOVA cannot handle unequal variances. All right? ANOVA cannot handle that. So we'll have to learn how to address situations when we violate these assumptions. All right, so let's get this in here. I think some of you are frantically typing. Let's get this in here. All right, so we finished up our t-test. Let's go through ANOVA. Analysis of variance. All right, so this is also ANOVA. Test if the means of multiple groups are equal. All right, that's what we're testing. Requirements. One qualitative variable. So nominal or ordinal can work. And we can have two or more groups inside of that categorical variable. We can have 20. We've done that. It just becomes hard to detect differences or identify where the differences lie. So we have one qualitative variable with 2 plus groups. This is our dependent variable. And then we have one measurement variable, one quantitative variable. So this could be continuous or discrete. All right, and this is our independent variable. Our null hypothesis is that all means are equal. Fairly simple. And we could say mean of group 1 is equal to mean of group 2, which is equal to mean of group 3. But if you have 7 groups, then you've got set all 7. So we're really just testing, our null hypothesis is all means are equal. And then our alternate is that at least one mean differs. And that could mean that all of the means are different. It could just mean that one of them is different. Right? So if we go back to doing like Poisson or binomial distributions, we had that question of, at least one. Same type of situation. We say that at least one because it could be 1 or 2 or 3 or 4, etc. With our means here, we're saying at least one mean differs from the rest, but we can have one mean that's different, two means that's different, three mean, etc. Assumptions. Well, actually, test statistic is F, all right, from the F distribution. Degrees of freedom associated with that is df1 and df2. So df1 refers to our numerator, and df2 is our denominator, because the F represents a ratio. And I'm presenting it as our signal to noise ratio. We're detecting the signal that tells us that the means are different. Now, if all of our assumptions are met, then our test statistic, that mean squared term, will approximate this F distribution. So our assumptions is data are random and independent. Second assumption, data are normally distributed within each group. And three, data are homoscedastic, which means variances are equal. Variances of the groups are equal. So, with our assumptions, I'm just going to add a little bit more. We test this with, or we basically adjust our collecting protocol. So data collection methods will usually ensure data are random and independent. For normally distributed within each group, we're going to use QQ plots. And we can use it as a formula. And if we get to a situation where you want to make individual plots so that they are large enough for you to see, I can show you how to do that as well. Then our last assumption is that data are homoscedastic. And our tests will either be a Brown-Forsyth test or, so we're going to run a Brown-Forsyth test if we have normal data. So there's going to be a step here. We test normality. If it's normal, then we can use a Brown-Forsyth test. If we're non-normal, then we'll use a Fligner-Killeen test. All right. And if we are ever in doubt about this, then you can always run a Fligner-Killeen, knowing that this is a non-parametric test, so we'll have less power to detect unequal variances. So again, if all of our assumptions are met, we'll follow the F distribution, and then we could use the F distribution to calculate the area under that curve to get our p-value. Do we have to do all of that? No. R will do it for us. Assumptions. So reporting. All right, reporting. We have to report our conclusion, interpretation, our test, test statistic, degrees of freedom, both of them, both DFs, and PA value. So degrees of freedom, we need both. We need the numerator and the denominator so that somebody can take the F statistic, plug it into the PF function, calculate the p-value, or look up a statistical table to figure that out. All right, I'm going to put this in bold, post-hoc test. So if p is less than 0.05, then at least one mean is different. We then have to figure out which mean or means are different from the rest. All right. So if all assumptions are met, then we'll run two keys post hoc test, we'll call that. If we violate our assumption, then we're going to have a couple different things we're going to do. Right? And there's another test that we can run if our assumptions are met. And I think I'll add it. So all comparison of all means, that's our two keys post hoc test. Or we can run a Dunnett's test, which is comparison to a control. So I will talk about that because some of you might be doing like molecular biology or microbiology where you have a control situation and then you have various treatments, and you're not necessarily interested in comparing between the treatments, but you're comparing the treatment to a control to see does the treatment have an effect. The Dunnett's could work for that. And I'll show you how to do those. If we violate the assumptions, I'll then have to show you how we do those. I'm not going to write them out here. We'll address those again when we start to violate our assumptions. All right, so let's go through our example. Plant growth is in the data sets package. All right, so it should be accessible just by typing plant growth. What I'm going to do is do question mark plant growth, and note the capital P and capital G. But I'm going to run that question mark plant growth just so it brings up the help file. And we can take a look at what this is. So this is an experiment on plant growth. Right? It's going to compare yields based on the dry weight of the plants under a control and two different treatment conditions. All right, so we've got a control and then we have two different treatment conditions. We have a data frame, that's basically what it is, 30 cases on two different variables. And the two variables are our continuous variable, that's our measurement, that's going to be weight, and our categorical variable is the group, which is a factor level variable, and it's control, treatment 1, treatment 2. All right, so let's take a look at this real quick. We did the question mark. I'm just going to look at plant growth, see what the first 30 rows look like. That's what they look like. So what we're going to do is I'm going to create this question. Does plant yield differ between our treatments? That's going to be question 1. So I'll do Q1 for question 1. And I'm going to have a second question here. Does plant yield differ in our treatments versus the control? So 1, it just looks at all of our treatments, our control and the two treatments. Is there a difference? The second type of question phrases it a little bit differently. Because now it says, does our yield differ in our treatments versus the control? Now we're placing less emphasis on comparing treatment 1 versus treatment 2, and more emphasis on comparing treatment 1 to the control and treatment 2 to the control. And that kind of helps determine what type of post hoc test we'll be running. So in parentheses, we're going to say 2 keys here, and then for this type of questions, we'll talk about Dunnett's. So that way we can see it. All right. So I have that here. All right, and I have lay out beginning of the script. This is all up in our test. All right, and I have making a figure. So the first thing we like to do is just go ahead and make a figure. And the figure that R will make is okay. However, I don't think box plots really does it justice. So first thing we're going to do with our data set is inspect the data. So what we're looking for is obvious departures from normality and equal variances. Also, where we are forming preliminary judgment on if the means are equal. All right, that's what we're going to do. We're just going to look at our data. So in R, we can just use the plot function to look at the data. So we can do it numerically, or we can do it graphically. I like to do it graphically. So I'm going to do a plot. We have yield as a function of group. Data is plant growth. I think that's what it is. No, let's see. Got to go back to my group name. Weight and group. I think I'm going to make it a little bit easier. Let's see here. Plant growth. Let's issue the data function. Plant growth. Package is data sets. There. I'm going to do that. I'm going to copy this and paste it in my library. Even though data sets is already loaded, it gets this promise on there. So the first time I use it, it should pop up in our environment. Do that. It should pop up in our environment. So now when we drop it down, we can see what our names are. Just a trick. You don't have to do this, but it's just kind of a trick. Because again, I couldn't remember what those variable names are. But we have it. Yep. All the way up to that top? Yep. Here it is. Let me highlight it. That's our spot. Data, plant growth. So the plant growth data sets is already loaded. It was accessible. I didn't have to load any packages. It's there once R starts. But it's not going to show up in the environment window because it's already just kind of built into memory. So by issuing the data command, it's saying, hey, get this in memory and get it in front. So it appears in our environment window. And that's just a little bit easier for us. So we can know, or we know what like the weight in the group was. Did it work?
It says data sets not found.
Oh no. Did you capitalize it? Did you put it in quotes?
Yeah.
Oh, packages. Package. Try that. There you go. Did you get the environment? Did yours pop up in the environment?
I thought I had a load card data.
Save it and then reopen R. Because it's looking like yours isn't loading. The environment isn't populating. Did your guys' pop up on the environment window?
It popped up on the environment window, but we're having a problem with yield not being found.
Oh yeah. It's not, because it's weight. That's what I was getting ready to go change
Okay.
when I scrolled down.
Oh.
Yeah, that was the issue. I had yield. No, it was weight. That's our variable. So weight is a function of group. Date is plant growth. And that's the yield didn't work because I couldn't remember it. But if it's up in the environment window, it's there. I don't have to kind of go back and searching for it. So this is pretty good. This is pretty good. But this is a median, right? So I look at this, I have control, I've got treatment 1, I've got treatment 2. So just offhand, if we were to run a test to see if means are equal, what would you expect? What do you think? What do you think?
It would be,
Okay, why not?
but if two is really high, what if you higher than the other?
There's a lot of variation. And if you do the response, is it silent over noise? Is that what it is?
Signal.
Signal over, yeah, it'd be not close to one because.
Yeah. So I look at this and say, it does. It right now, I'm looking at like the middle at these lines. These are medians, they're not means, and that's one of the problems with the box plots. But I look at it. If all of our means are equal, then our lines in the boxes should kind of line up in a horizontal line. And they're not. This one's a little more than 5, this one's down by like 4.5, this one's near 5.5. This is looking like we may have a difference in mean. So if I run the Anova and get a p-value that's less than 0.05, I'm not going to be surprised. I'm not going to be surprised. So based on the figure, it looks like the means might be unequal. The assumptions are harder to assess. All right. They're harder to assess. So our assumptions of equal variance and normality. With our normality, we said that if we're normally distributed, then this box should be in the middle, right? The more our this line should be in the middle. If this line is moved closer to one side, tends to indicate skew. However, look at our sample sizes. We've got a total of 30 values, which means we probably only have 10 values in each of these. So 10 for the control, 10 for the treatment, 10 for the treatment too. So I'm going to say assumptions are harder to assess, but they might be met. Maybe. What about calculating means and SEs? So I type that down. I need to go up and check to see if I loaded my function. No, I did not. So back up to the top. I am going to add my standard error function. So go back to my function script, copy it, paste it. I'm going to run it. So STERR is now accessible. So figure can work, but maybe you want to know the actual value of the means because the box plots are plotting medians. And in the write-up, you probably want to list the mean someplace. Well, we're calculating a mean for each group, and the function that we can use is called aggregate. So we'll use the aggregate function. All right, so the code is aggregate, y is a function of x, data, and then fun equals some function. All right, so this is y is our dependent variable, x, that is our categorical variable, our independent variable, so that's categorical in nature. Dependent variable is measurement in nature. Data, that's our data frame, where we find x and y, and fun equals mean tells R to calculate the mean. And we can pass additional things to it. So like the mean function has na.rm, we can pass that to in this function. So I can add this ... just like the R help files do. and specify that this dot 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 is extra options that we can pass to the function, to fun. And fun is capitalized. So for this example, this code will apply the function, whatever function we tell it, to the y variable for each group in X. That's what it's going to do. So if we have the mean function, it's going to apply the mean to our y variable for each group in our categorical variable. So our example for us is to use the aggregate function. We want weight as a function of group. So we're going to calculate the mean weight for each of the groups, for each of the levels in group, where our data is plant growth, and the function that we're going to apply is mean. And I'm going to leave off the na.rn because we know that this data set does not have any missing data. So now, here's our means. How do we do this in Excel? Well, you have to have the data there, and then you could do equals average and then highlight the range of the average. That's not bad. You have to type it in multiple times, or you have to rearrange your data set so that each group is in its own column. Here in R, if we have one big column with our measurement variable and a second column for our grouping variable, we can utilize the aggregate function to get this. I should also say you can use pivot tables as well in Excel. That's like another few classes to learn how to do those. So here's our mean. They're probably close to our medians. You can see we've got about 5, 4.6, and then 5.5. So these look pretty different. But our difference comes down to the noise, which we can use for our standard error. So I think I had said, there's a reason why we wrote a function for the standard error, and it's so that we can put it here. So if we wanted to make our own figure in Excel, and we're comfortable making figures in Excel, we can use the aggregate function to get the mean. We take these values, type them into Excel, and then we look at the standard errors, and we transfer these over to Excel, and these would represent our error bars. So the units above, 0.184 above, 0.184 below the mean for group A, 0.25 above, 0.25 below, and so forth. If you're curious on how to make a figure in Excel, doing it this way, I do have a YouTube video that you can check out that shows you how to make it, how to basically take a mean and standard error and add over error bars to it. It should probably be updated to the newest version of Excel. Or actually, probably try to use Google Docs. Probably what I should do. More and more people. So, there's our data. All right, so box plots are okay. That's what we have. I modified them a little bit so they didn't shade. Or this was an original version. But we've looked at the data. It looks pretty good. We also look for outliers. I should say that. The graph shows us outliers. Yeah, that points out. We're really looking for those points that are way up here, where all your curves are really compressed right down at the bottom. You've got that one point out there. Probably have a typo. Go back and look at that. This one's 6.0, but if you forgot the decimal and you keyed it in a 60, it'd be way off the charts. All right, so our question, does the means differ? We know we want to run an ANOVA based on the underlying data. We have a categorical variable that has 3 levels. We have a continuous variable, that was measurement. All right, so our next step then is to check our assumptions. All right, so our next check is to check the assumptions. So we're going to check our assumptions. Actually, I think this is 3. Checking assumptions. random, first is random and independent. Assume this is true. So first thing is data are random and independent. Assume that it's true for this class. We'll leave it at that. Normality, we'll use QQ plots. And this is where we did things a little, the handout has subsetting. We're going to get to subsets again, but I think we're just going to use the QQ plots because we've already showed you how to do that. So QQ plot, we're doing weight as a function of group, and the data is in Planck growth. And this generates a QQ plot for every group. And I think it's big enough to where we can see every single one. Right? So do you think we met the assumption? Yeah, with 10 data points, you have to really be skewed. Not just skewed. I think normally what you would get is a difference of scale, where you've got one group that spans a very, very large range. I think that's when you would start to see some differences.
Why are your envelope shaded?
I had no idea.
Oh, alright. So the box and whisker plots aren't always reliable?
No. Nope. Because it's based. Like if I go up to this box and whiskers plot, I would be tempted to call that one skewed.
So it's
Right.
like the histogram, like you
Yeah, but if we look at the QQ plot for that group, yeah, they're all in there. It's good. Which we'll look up. QQ plot. There should be a shading option here. Layout. We can change the layout if you wanted to. And I've done that before. Color for points, color for lines. ID. The envelope argument can take a list. Yeah, maybe that. Let's try that. So if we do envelope equals a list, style is none. Let's try that. Oh no, that's not right. Line. Let's try lines. There it is. That's not the greatest. Alpha. That's what yours looks like?
Mine says it doesn't really keep the files.
Capital P? Did you load the card library?
Yes.
That one's okay. It's okay, but it has the lines on the end.
Right,
Yeah. I think. Yeah, hers was just the lines. Why is that the default? Filled is the default.
Which version?
Yeah, that's good. I don't know. I don't
You're
know.
probably running a slightly different version of R than what they have loaded on the rest.
Let's check it. How do we check that?
And I noticed whenever you start up, it'll say the version at the top of the console. So the one that I have is funny when you freak out. So if you scroll all the way up to the top of the console.
Citation. No, citation just gives the citation. Yeah, it's at the top of the console. You're right, that's normally what I get. I get 4.0.3. Is that what yours is?
And it's funny when you freak out.
But we also have the car package, So the car package is 3.0-11.
4.11.
4.11.
At 3.0-10.
That's fine.
Great. Yeah, differences. That's okay. It's okay. We've tested.
Then you get the point across. We know.
Yep.
We know what's going on.
All right, so normality QQ plots, we look normal. All right, that's good. So our interpretation conclusion for this one is that data appear to be normally distributed within each level of group. I don't like to say group because the name is group, but within each level. So the control, treatment 1, treatment 2, they all look to be normally distributed. All right, next assumption is equal variances. Or same thing as homoscedasticity. All right, if data are normal, run Brown-Forsyth. If data are non-normal or questionable, then we're going to run Fligner-Killeen test. All right. That's what we're going to run. So we're going to do the Brown-Forsyth test since we're normally distributed. And we're going to set up another one. And I'll show you how to do the Fligner-Killeen because, again, Fligner-Killeen you can run even if we're normally distributed. The problem is that Fligner-Killeen is a non-parametric test and has less power to detect the unequal variances. So we prefer the Brown-Forsyth test. All right. This test tests if the variances in multiple groups are equal. All right, that's what our Brown-Forsyth test is going to do. Our null hypothesis is that variances are equal. Our alternate is that at least one variance is different from the rest. Now, unlike Anova, so this is similar to Anova, but it's with variances. But unlike Anova, we don't care to find out which variance is different. We're just using this to determine if our assumptions of Anova are met. All right. Brown-Forsyth uses the F statistic. It's going to be the F. Degrees of freedom. It's going to be a DF1 and a DF2, and we have to report both. The assumptions of this test, again, data are random and independent. Data are centered around the median. So here's the interesting thing about our test. We're going to do an omnibus test, one test that's run on our data to determine if we need to go further, if we need to start taking subsets and breaking down our groups. If, for that omnibus test, we are random and independent, normally distributed, equal variances, then those assumptions will hold as we break down and do small subsets of our data. We've already planned for random and independent. This assumption we haven't really checked, but we kind of did. Because if we're normally distributed, then our data are centered around the median. It's just one of those definitions that if we're normally distributed, we're not only symmetric around the mean, but we're symmetric around the median. All right, so this assumption is met when normally distributed. And this is why when we check for normality first. If we're non-normal, we could still be centered because we could be platykurtic or leptokurtic, but more than likely we'll be skewed, in which case this won't apply. I guess centered, probably symmetric might be a better term. And it's our values. Right. So those are our assumptions. They do have assumptions. Reporting, conclusion interpretation, our test statistic, degree of freedom, both DFs and p-value. Our code. Of all the things that we run, this is the one that might throw you off. Our code, Levine test with a capital T. Y is a function of x, data, and center equals median. Right, so with this, y is a function of x, and data, same as Anova. Same as all of our formulas, all right? Just standard. Center equals median. This runs Brown-Forsyth. Center equals mean runs Levine's test. We won't use that. All right, so I present this because it gets to how we test for variances. Levine came up with the first test for equal variance. It's measuring your dispersion around each of our group means. All right, so it's centering our data on the means themselves. The problem with this is if we are even slightly non-normal, it throws off our test. It increases our error rates. So then Brown and Forsyth looked at it and said, hey, well, if we change, if we center it on the median, it improves our reliability when we're slightly skewed or when we're slightly non-normal. So we sacrifice a little bit of power, not much. We sacrifice a little bit of power to improve reliability in determining or making this claim and testing these hypotheses, or this hypothesis. All right, so we're going to use center equals median to run the Brown-Forsyth test. So for our example, let's look at it. For plant growth, we will use Levine test. We have weight as a function of group, data is plant growth, and center equals median. I am going to note here that Levine test up in this R code found in the car package. So this is in the car package. Kind of very useful. So I'm going to run it and we get this output. Now it says Levine's test for homogeneity variance, because it is. Brown-Forsyth said we're going to run the exact same test, but instead of centering our data on the mean, we're going to center the data on the median. With the idea that if we kind of have everything centered on the median, and if we have equal variances, then when we count up our number of data, we measure how far our most extreme data points are from the median, they should be equal among our groups. So we have the name of the test. It's the one catch. We're testing for homogeneity of variance, but it's not Levine's test anymore. And we know it's not Levine's test because we're centered on the median. And that is actually in the help file too. The help file will tell you this. So we run Brown's Forsyth. We've got our test statistic, that's our F. we have our degrees of freedom. 2 values are listed, 2 and 27. We're going to have to report both of them. And then we have our p-value. So our write-up for this part is that our variances, the variances between the 3 groups are equal. And we ran a Brown-Forsyth test. Our F statistic is 1.12, and there's we rounded 2 decimal places because that's our test statistic. And then DF1 is 2, and DF2 is 27. So we have to report both. And then our p-value is, I'll just do equals 0.34. Now, I don't like this because we're doing DF1 and DF2. But we can get around that by doing our subscripts. So for the F, I can put as a subscript 2, 27, and that is sufficient to tell me both of my degrees of freedom. So when you asked, hey, why I didn't use DF, it was because I put it in the subscript. That was earlier today. Well, here it is again. I'm putting this in as a subscript. So F and then subscript 2, 27. That tells me exactly what my degrees of freedom are.
Do you care if we don't?
No, I don't.
That would confuse me a little bit.
I am looking to make sure that you include all 5 things that need to be reported. But you will lose points if you only give me one of these. If you say DF equals 2, that's not going to work. I guess you can also do DF equals and then brackets, or curly braces, 2, 27. That could work too. So I guess we'll do that. Or DF equals curly braces 2, 27. I'll accept that. I don't think journals will accept it. They prefer the subscripts, but if you do it for the write-up in this class, I'll take it. I think we're good. All right. 3, checking assumptions. All right, so we have now checked all assumptions. All right, all assumptions are met. So we can run Anova. So all assumptions are met, we can run Anova. This is going to be a 2-step process. So this is a 2-step process. First, we make a linear model using LM function. And we're gonna say mod, and because we're gonna save it. So we're gonna create a linear model of our data. That's going to tell R, generate your best fit equations. Generate your best fit equations, and also calculate your sum of squares. Because those best fit equations, like in Excel where you add a best fit line, it needs those sum of squares values. So it'll create this model, and then once we have that model, view the Anova table of the model using Anova mod. And note, capital Anova is in car. That's in the car package. There's also a lowercase Anova, which will work. But I'm prepping a graduate student for 2-way, 3-way, 4-way Anovas, where the capital Anova gives us more control over how we create our Anova table. but either one will work. So this is our two-step process. So for Planck growth, this is how I run it. So I'm going to call it mod 1, our first model. I'm going to create a linear model. LM is linear model, where it's weight as a function of group. It's everything that we've been doing. And our data is Planck growth. And everything else is good. And then what I'm going to do is look at the Anova table of that model. So I created our linear model, and then I looked at the Anova table, because it's the Anova table that provides all of the information that we need to make our conclusion. So when you run it, this is what we get. No, it is sum of squares.
Okay.
Yep, sum of squares, df, f value, and PR. PR of data greater than f. It's the probability that we would get an f statistic, an observed f statistic greater or equal to what we actually observed if our null hypothesis is true, which is our p-value. It's a definition of a p-value, that's what that is. So, items of interest. Items of interest, right, is Anova. That's what we ran. We have the f value, which is our f observed value. So Anova is just right up at the top. The f value column, that is our f observed, just like our t observed data. All right, we're going to report that. df is both degrees of freedom. And then PR parentheses greater f parentheses is our p-value. What are the other things? The sum of squares and the residuals. That is our variance. That's our measure of variance, how much variation we have around our group mean. Group means, that's our residuals, that's our error. And our group, which is our signal, that's our treatment. So residuals is the error part. The group is our treatment, or signal. All right. But again, these values are sensitive to sample size. So as we keep adding samples, the number should get larger and larger and larger. So instead of utilizing the raw sum of squares, we use our mean sum of squares, the MS value, by taking this value dividing by the degrees of freedom. When we do that, when we divide by the degrees of freedom, then we get our signal and we get our noise. So you can say, well, the noise is actually larger. It's 10.5 versus 3.8. But when you take 10.5 and divide it by 27, you get an even smaller number than this. How much smaller? Well, almost a fifth. So this represents our signal to noise ratio, which is actually fairly large. So based on this, what's our write-up? So if one, what's our conclusion? Are the means equal? Are the means equal?
If the PR is greater than f and that's the p-value, is that true? Or
Accept what?
the null hypothesis?
Have we ever accepted a null hypothesis when the p-value is small?
Yeah.
No. Okay. So what's our cutoff? What's our p-value cutoff? What's that? 0.05, right? All right, so are we less than 0.05?
Yes.
All right. In all cases, whenever our p-value is less than 0.05, what do? We rejected our null hypothesis. What's our null hypothesis? Our null is that the means are equal.
Yeah.
So if we reject that, we know the means are not equal, right? There's our answer. So 0.05, set it up at 0.05. All of our null hypothesis is that no difference. No equal variances means variances are the same, means are the same, all of that. And then it's 0.05. If we're less than 0.05, they're not. They're not the same. So yeah, our write-up right here, we know is that our treatments do have an effect. Now we don't know what the effect is, right? So instead of saying our means are different with 3 groups, it's probably best to say our experimental treatment affects plant weight. Treatment affects plant weight. And that then implies that our plant weight depends on the treatment. So our write-up then includes, so that was our write-up, our conclusion or interpretation. Our test is ANOVA. Our test statistic is 4.85. And I'm going to use subscripts for the degrees of freedom, which is 2,27, which incidentally is the same subscript, or the same degrees of freedom as Brown-Forsyth. And then our p-value, say less than 0.02. So now, we know a difference in means exists. Our next step is to determine which means different. From the rest. So it could be that all are different, it could be that none of them are different.
Didn't we just confirm that one of them had to be different though?
Yes, so that's what I said. One of them can be different, or all of them can be different.
Okay. I
So
thought
we
you
had-
said none, not one.
Did I say none? Maybe? None?
I heard
One?
Is this something around the QQ plot now?
What does the QQ plot do? What did we use to test? Short answer is no. What do we use? Our QQ plot is used to test normality. So we know our data are normally distributed. We know we have equal variance. So everything now, we did our Omnibus Test. We used the entire data set. What we now want to do is break it up into individual groups and start doing pairwise comparisons. So we're going to start doing repeated tests on the data. Those assumptions are going to be the same. Equal variances, normality, but we've already tested it in the bigger data set, and if they hold in the bigger data set, they're going to hold. We assume that they hold below us. So now we're going to use a post hoc test. So we're going to use a post hoc test to address this. The type of test depends on, I'm going to say, the a priori question. All right, so that's why I did question 1 and question 2. Because those questions tell us what type of post hoc test we should run. All right, so for question 1, so this will be post hoc test. We're going to start with Tukey's HSD test. That's what we're going to start with. So post hoc test, Tukey's HSD test. This compares all means. It's going to compare all means to each other. And while we're at it, because we're getting close to finishing up, Dunnett's test, that's going to be our next one. It's going to compare only the treatments to the control. So it's not going to test They're compared treatments to each other. It's always treatment to a control, and that's it. I rarely use Dunnits because I'm not setting up control and then various treatments. I typically use 2 keys, but that's not to say that you'll always use 2 keys. All right. Questions? All right. So, a couple things before we break. So we did have this. We didn't talk about subsets. We will get to subsets. No big deal. This was again differences in. We didn't do the Fligner-Killeen test because we met. We have to do that. Our assumptions are met. We did skipped a lot of this stuff because I don't really think it's valid, or not valid. It's not. While it's important, I don't really ask those questions.
Not particularly useful.
It can be useful. I just don't ask those questions because it's limited. It's limited on our usage. So yeah, before we leave, let's go over the Fligner-Killeen test one time because I did forget that. So we did Brown-Forsyth. So after the Brown-Forsyth, we're gonna use Fligner-Killeen test to introduce this. All right. So copy all of this. Fligner-Killeen is built in.
Where else did you copy?
I came up here to the Brown-Forsyth and I just copied all the way down to the R code. And I'm going to update it. Because the questions are the same, the null hypotheses, alternate hypotheses are the same. Our test statistics are going to be different. And our assumptions are going to be a little bit different. So it tests if the variances in multiple groups are equal. That's what it's testing. I'm going to add that this is a non-parametric test and compares ranks instead of actual values, like the weight values. It's not going to use the weights. It's going to convert the ranks or the weights into ranks and basically order the data from the low rank up to the high ranks. All right, and number them 1, 2, 3, 4, 5. So we eliminate the actual value of the weight and utilize the ranking, which is making it non-parametric. All right, so the end result is less power to detect a difference. Between the variances. So that's going to be our effect. And it's just kind of like the sign test. If we had a sign test that had a p-value of 0.06, 0.07, how do we know that our values, that our x is actually equal to the mean, or that our x is equal to the median? How do we know that that's a conclusion, not that we just couldn't detect difference because we're not powerful enough? Same thing here. If we get a p-value that's close to 0.05, 0.06, 0.07, it could be that we don't have enough power to detect the unequal variances, or it could be that we are actually unequal variance. So our null and alternate are the same. Our test statistic is a chi-square. It's going to be a chi-square test because it's going to generate like observed and then generate expected chi-square value. So our test statistic is going to be chi-squared. Chi-squared test is defined by degrees of freedom. Then our only assumption is that data are random and independent. Since we're working with ranks, we're not as concerned. And this is why if we meet the normality assumption, or if we violate the normality assumption, we can run this test because it doesn't make that assumption. So we're going to report our conclusion, interpretation, the test statistic, degrees of freedom, and our p-value. So the code it's in. Actually, I won't even say it's in the base package. It's built into R. We don't have to do anything special to it. Our test is Fligner.test. Y is a function of x and data. And I'm going to copy that. I've already kind of said y is a function of x and data, same as Anova. That's all it is. So for us, I can run Fligner.test, weight as a function of group, data is plant growth, and run it, and this is our output. And we can't really compare the p-values to the Brown-Forsyth. The only thing is we look at the 0.05. Are we less than 0.05? Are we greater than 0.05? So for here, our write-up, are we greater than 0.05? Yep. Our null hypothesis is that they're equal, so we failed to reject that, and thus conclude our variances are equal. And then our test, Fligner-Killeen test, and then our chi-squared value is 2.35. Degrees of freedom is 2, and a p-value is less than 0.3. And it, like in Word, I'd make the subscript. I had actually used the chi, the lowercase chi, and then the square. And we can use the degrees of freedom in the subscript. We can do that as well. But then you have a superscript and a subscript. So that's our Fligner-Killeen test. You can always run a Fligner-Killeen test, but no, we have lower power. So if we're normally distributed, Brown-Forsyth, that's what we run. If we're not normally distributed, run the Fligner-Killeen test. All right, so a couple things. Tri-betas are running a blood drive. That's on the 30th, maybe? 30th? All right, so if you donate, or if you try to donate and get turned away, or if you recruit someone to donate, then I'll give you 5 extra credit points on the 3rd exam. That'll just be over our overall. If you know that you can't donate, come talk to me. I know Tri-betas always have volunteer opportunities, so we can make that as a possibility.
This is they'll have volunteer opportunities later.
There is. If you can't make it on the 30th, you can always donate someplace else. So if you go to the donor center, you can fill out, hey, I'm donating for the Tri-betas, I just couldn't make it there. They'll give you a sheet that says, thanks for your donation. Show me the sheet, it has your name on it. There's no personal information, it's the do's and don'ts. Like, relax, don't exercise, drink plenty of fluids, call us if you get sick, that sort of thing. Then we also have the IDEA evaluations. You're gonna get nailed on emails until you take it. All right, just constant. That's gonna be, so I do have it set up, so as soon as we hit 50%, then we'll start doing extra credit on the final exam. All right, the goal is to get to 90%.
When does the IDEA survey over this year?
Next week, I think.
Okay.
I think it's open for 3 weeks. I think is what I've heard. So 3 weeks would be next week, because it would be next week, Thanksgiving week, the week after Thanksgiving. That would be your 3 weeks. It's not open this week, but yeah, we'll do that. And one thing some of you, I'm sure you've noticed, we've got the presentation and I do the stuff, but I've kind of drifted away to get the notes in an RMD file. That is new. I'm curious how this method worked to get a set of notes, or if it would be better just to kind of go back to the PowerPoints that has all of the code and stuff. Because if it goes for more of this, I can streamline the actual presentations to where it's like, see the RMD file or something like that. So I'm going to be curious to see what you think at the end of the class. I am curious about that. All right. Personally, I like this. If I was doing the class, I'd like this better because I have everything there. I'd like it until my thumb drive dies on me.
Yeah, I like that one.
I like this because like you go more into depth into explaining.
Okay.
Yeah, and it also just flows better. Like there's not that disconnect of waiting for PowerPoint to get pulled back up.
Yep.
And it's something that happens when you have to flip tabs.
Mm-hmm.
Whereas when you're just taking notes all at once.
Okay. Okay. So look at that. Maybe a handout instead of PowerPoint. Handouts with definitions.
Yeah.
Or like an outline of what you do. Maybe an outline. Okay. Well, let's see what we can do. All right. So I'm going to tell you, this Anova is going to be on our exam. All the way through our post-hoc test. We'll do the post-hoc test on Wednesday. I'll show you both. 2 keys is easy. Dunnits is a little bit harder. We'll have to load another package. But we also have, I have example data set, fish data set that we'll practice. So I've got everything. Yeah, fish length that we're going to work through. So on Wednesday, we should have finished up all of the post-hoc tests, and this fishlength.txt data set is posted. I'm going to ask you to do the Anova step through checking the assumptions, running the test, doing any post-hoc tests you want, and we're going to go through this on Friday as kind of a prep. Our exam on Monday, I've already kind of decided the 11 o'clock lecture, that's when we'll do our closed book portion. And then for the lab, we'll do our application, so we've got the full 2 hours. So I think it'll take the full 2 hours? No, I don't think so. Just like I think for that 11 o'clock time slot, we shouldn't take the full 50 minutes.
You're not going to do as many questions then because you have to run some.
What do you mean?
I feel like you have to run a lot because you have to.
So less questions, more parts in each question.
Yeah.
Mm-hmm.
Okay.
Yes. So the closed book part, I might set up scenarios to say, okay, you're checking assumptions, normality was violated. What is the next test that you run and why? So you're getting a flow chart. Like, here are my steps. I just checked normality, we violated it, now I have Fligner-Killeen or Brown-Forsyth, right? Which one do you choose? So yeah, that's kind of like the closed book, just to kind of follow that process. And then in the application part, I would tell you, check the normality assumption using QQ plot. Check the assumption of equal variance using Fligner-Killeen or Brown-Forsyth. And then run the Anova, run the post-hoc test. On the final exam, and I don't think I necessarily do this one, but on the final exam, there is a question where I don't tell you what to run. It's just, here's the question, answer the question. Here's the data, answer this question. Are the means equal? Yeah. That's really what it is. Are the means equal? Then you have to kind of step through the process and make the correct choices. So that one's kind of like not only demonstrating that you can do this stuff, but also following the correct process. Yeah.
Hopefully Charnada knows there's another volunteer program for finals.
All right. And let me go through here. I did look at the exam, the redo. I'm going to release the grade so you can see it, but I'm not going to release the keys yet. You can take a look at it. And I did look at, I think grades improved. Hopefully it kind of got you back in there looking at this stuff. should be viewable. So the score in Blackboard is out of 40 points. What you would have to do is divide that value by 40 and then multiply by 50 to get your replacement group. Make sense? Because we're scaling it out of 50. So you take the score of Blackboard, divide by 40, multiply by 50. And that gets it to a score out of 50. So yeah.
Before you did whatever you just did, I could see my score. I can't. For the redo part.
Reload. Because on my end, it shows that it's visible.
Yeah.
Yeah. Well, the first time I did it, nothing changed. So then I did it again, nothing changed. Did it again, it worked.
How desperate are they for blood? Because last time I tried to give blood, they didn't want much.
It should be desperate. I'm getting blasted. So
I am too, but my iron don't.
so when you try, they're gonna deny you. So that is why they have that why they have that. I have no idea.
Like my iron's always been low. It's just how much it is.
Yeah.
I don't even know what my blood type is.
I mean, there's other things that it's like, if we could go by all of our requirements here in the U.S., like globally, no one, like, you've got like the vast majority of Europe can't donate blood.
My dad's O negative and RSV negative.
Yeah.
They want his blood. They constantly, he's like, I can't, I just gave you my blood.
So they are, there is a shortage.
At this point, when I go on like, I just before I fill out anything, I need you to check. So I don't have to fill out anything or hold my hand.
Yeah.
What if that is?
I haven't tested positive for COVID, but for people that have, are they allowing them to give blood?
Yeah, they're
Wanting it more? Or?
I think it's 28 days since symptoms. So yeah, I was blocked out because my wife had it, so I had to wait 28 days before I could donate after she had it. And then it was a good thing because I tested positive like 7 days later. And then I had to wait 28 days. And then after that, it was no symptoms. So yeah, that's good.
Will they tell you if you have antibodies?
Yep.
They will?
Yep.
Sweet. I'm gonna go down
They'll tell you if you have antibodies.
because I'd like to know. But I've been vaccinated, so I'm sure I have antibodies. Never mind.
No. I mean, like,
Did you get your titers checked? I don't know if they check titers and blood donations, but
All right, so
there's some groups that get their titers checked pretty regularly to see if they need boosters or not. I mean, I know you think you're serious.
I was curious if I had been exposed before and just didn't know it.
yeah.
You said you give us extra credit for volunteering for SWAT.
But like, we're.
Yep.
Okay, because I don't have a car, so there's no way to go donate otherwise.
And they were like, okay.
Yep.
I had to go volunteer practical that day, and we might have kind of blood for taking practical. Really isn't the greatest idea. All I know is the last time I tried to donate blood, they pricked my finger and I passed out. I have blood or just in general? Just in general. Just in general. I have really bad anxiety, so I overthought it. The only time that I haven't passed out when they take my blood is when I was in so much pain I didn't care that they were taking my blood. And when they efficiently distracted me in the doctor's office while I was lying down and facing away from where they were going. Yeah, blood draws are close. So Dr. Nicoletis, if you're doing an outline, you should make sections where whenever you do board work, that people can, that's one of the things that I think is throwing me off too.
Yeah.
Is I have to like sit here and shuffle and find a sheet of paper.
it's a good idea.
And when I was using the post-doc PowerPoint, there still wasn't room to do it on the PowerPoint.
There are
My
some.
notes are all scattered.
So I think value for the PowerPoints is just early on where we just kind of go over definitions and that's about it.
Yeah.
And then once we actually start getting to the applications, it's probably better to switch to R&D because we get our notes and we get the code examples. A little bit easier to do it all here than everything else. And I might be able to do kind of strip it out, streamlined it. So you've got, like, for here, here, when we get this part, that could be in like the R&D file. So it's there, we don't have to type it out and copy it. Here it is. Now let's talk about how we actually do it. Let's talk about the interpretation. So we have it.
And we can make additional notes on it as needed while you're talking about it. Because one of the other things that I'm noticing is I don't have as much time to say something and I want to add it. I have to remember it and add it to what I'm typing and copying.
Okay.
Especially if it's not stuff on the board that draft. They're all in control.
Oh, yeah.
I just don't know you.
All right, we're good. We're good. I'm gonna get the homework key and posted. So you can look at it.